Welcome again to Helicopter Training Videos. In this video we're going to look at helicopter flight controls. Back in the early days, helicopter designers were managing to get these early helicopters off the ground, but they were struggling with the ability to actually control them, to get any sort of directional control out of them. This early helicopter, this is a 1907 Cornu helicopter. This aircraft could become airborne but had no lateral controls, and many designers gave up with that idea and went on to work on other projects. By 1936, the control problem was essentially solved by Fokker-Wulf with his FW61. And at the end of the presentation we'll have links to a video of that being flown indoors. And by 1949, so much progress had been made with helicopter controls that people were able to loop helicopters. We've got a link at the end of a video of a Sikorsky S-52 being looped in 1949. So today we're going to look at the collective, cyclic, anti-torque pedals and the throttle, including the correlator and the governor. Let's go out to the helicopter and have a look.
Okay, first we're going to look at the cyclic, and there's primarily two designs of the cyclic. There's the T-bar, which is what we've got here, which is what Robinson favors, and then the other design, the more traditional design maybe, is the one where you'd have a control stick between your legs, and you'd have one for each pilot. Robinson used this T-bar system because it allows the control to be here instead of between the legs, which requires less space, so the helicopter can be not as wide. It also saves weight on having two full control systems like that. And then what we have here, this isn't a steering wheel. This allows the pilot to switch the control over to the co-pilot or the instructor. It also allows the pilot to bring this control down, rest his arm on his thigh, and have very fine control movements here. So don't be confused, this isn't a steering wheel in any way. This does nothing. This just allows you to get comfortable and hold the position. And then if you watch my hand and this control, they follow each other. So although it's disconnected by this control here, they actually are doing the same thing. So what this control does is it tilts the disc in the direction you push. The actual rotor disc, it tilts in the direction you push. So if we're pushing forward, it would be tilting the rotor disc forward, backwards, left, and right. So that will control the pitch or the roll of the helicopter. What's actually happening mechanically is there's connections down here and push and pull rods and bell cranks sending the controls all the way up to the what's called the swash plate and onto the rotor system. And we'll talk about those in more detail in a future lesson, but the important thing to know is that this cyclic controls the individual pitch of the blades individually, and as it changes one blade, it'll be changing another one in a different way. We'll talk about that when we go up and look at the rotor head itself, and you'll see how that actually works. A couple of other controls related to this. We have this down here, we have the cyclic friction. And what this does is if I turn this friction all the way off, we have a lot more freedom of movement here. And we put the friction all the way on and tight, and there's very little movement here. This is used on the ground to keep the control steady until you're ready to take the friction off and go to flight. It's not used in flight mode. You turn the friction off before you fly. The other control we have in here is something called the trim, and it's this little thing here we can pull up, and when we've pulled this up, it puts a bit of pressure to the right on the cyclic, and the reason it does that is in high-speed flight the right side of the disc starts to flap up, and so we have to put in right cyclic to counter that. So if you didn't have this trim, you'd be flying along, say 80-90 knots, and you'd have to constantly put pressure into the right. And this trim just takes that pressure off, just makes it easier and less fatiguing on the pilot. Robinson recommends you always reach around to the left to do this control. Don't reach through here. And the reason is there's also the fuel cutoff control here, and people have inadvertently gone to pull their trim, and instead they've pulled the fuel cutoff, the fuel mixture, to the cutoff position, and they've shut the engine down. So always reach around to the left for your trim control. And you may see this little knob down here. This just adjusts how much pressure this trim puts in. Generally you leave it where it is. Okay, so there's a couple of other controls on this control switch, control column. One is the landing light, so on and off control for your landing light. And then if we come up to where the hand is, you've got a trigger on the front here, and this is your push to torque or your push to transmit. So if you're tuned into Redmond Tower, for example, you would push that and then you would talk directly to Redmond Tower over the radio and release. And the co-pilot or the instructor has the same control on the left-hand side on his. And we also have a frequency switch or flip-flop button. And what this does is it switches between your primary and secondary. It's the same, if you look down at the radio stack down here, it's the same as pressing this button here, and that's just switching your primary and secondary radios frequencies. And then also we have up here a channel select button, and this cycles through the 10 presets that you would have set in your radio. Okay, and then to the left of the pilot we have what's called the collective control. And what this does is this is like the up and down for the helicopter. So if we pull the collective up, it collectively increases the pitch on all of the blades at the same time. And so because it increases the pitch, it increases the lift and drag, and we go up. So down, up, go up. So if we're asking the helicopter to produce more pitch and more lift, we're asking the helicopter to kind of do more. If you think about driving in a car, you're driving along at 50 miles an hour, and as you come up to a hill, if you start going up that hill, if you don't put more throttle in, if you don't ask the engine to produce more, then you'll start slowing down. And it's the same here. So if we ask for more pitch and more lift, and we didn't do anything with the throttle, the rotors would start slowing down. And the way this helicopter deals with that is there's something called the correlator, which is a linkage between this collective control and also the throttle. So as we pull more collective, the correlator automatically increases the throttle, so it produces more power output with the helicopter to try and deal with the extra power demand we've asked for as we pull the collective up. Like the cyclic, there's also a friction control back here. So if we push the friction back here, it's now locked, the collective, and we bring the friction forward, it's now free to move. In some of the helicopters, these collectives kind of droop over time if you don't constantly hold them, and so some people put a little tiny bit of friction on just to hold it there. Robinson actually recommends we don't do that because if you think about it, if you have an emergency engine failure, you want to lock that down as soon as you can. You don't want any friction, so they recommend you keep that friction off. Down in front of the pilot we have these pedals here. These are called the anti-torque pedals, and the primary purpose of what they control is the tail rotor. The primary purpose of the tail rotor is to counter the torque of the main rotor system. And we'll talk about torque in more detail, but essentially it's about equal and opposite reactions. If you want to spin those blades around above us, the main rotor system, then the torque reaction will want to swing the helicopter in the opposite direction. And the way we counter that is we have a tail rotor which is thrusting against the torque reaction. And what these pedals do is they change the amount of thrust that that tail rotor produces. And so if I push left here, what's happening is, and we'll go and look at this in a minute, it's pushing the push rods and connections all the way back down to the tail rotor, and it's increasing the pitch. And by increasing the pitch on the tail rotor, it increases the amount of thrust. So this is what we would use to push the nose left, and it does that by increasing the thrust on the tail, which pushes the tail to the right, and of course pushes the nose to the left. And then the opposite way around, so we come back to centered, and now by pushing the right pedal in, we're reducing the pitch, and by reducing the pitch on the tail rotor, we're reducing the torque, reducing the thrust, and we're letting the torque take over, and that will swing the tail of the rotor, the tail of the helicopter to the left and the nose of the helicopter to the right. So in hovering flight, we use these to make what's called pedal turns or hover turns. So if imagine we're hovering right now and we want to push the nose round to the left, we push the nose round by pushing the left pedal in, center, push the right, push the nose to the right. Once we're in forward flight, we don't turn the helicopter using these pedals, we turn the helicopter using the cyclic by rolling the helicopter to the left and right. But these pedals are still used in forward flight because as we make changes to the amount of power we're asking, remember if we're pulling the collective up and down, we're changing the amount of power. By changing the amount of power, we're changing the amount of torque, and therefore we need to put in little adjustments to keep the helicopter what's called flying in trim. We want the nose pointing directly where we're flying. For example, if we pulled a load of power and we didn't make any adjustments, it would end up swinging the nose of the helicopter to the right. And so we'd end up flying kind of a 30-degree angle. We'd end up flying kind of feeling like we're falling into the flight. And we'll talk about that in aerodynamics in more detail, but these are used to keep the helicopter in trim. So what we have here, this is a pretty low-tech solution to that trim problem I was telling you about. It's just two pieces of string or wool, and the idea is when we're in forward flight, these will be pushed up, so they will sit up here, parallel, either side of here. Right now we're on the ground, we're not moving, we're being blown around by the wind, but the idea is they'll sit up nice and straight, and if we're out of trim, they'll tend to swing out to one side or the other. And so we know we're flying out of trim, we've changed our power setting, and we haven't changed our anti-torque rotor, tail rotor setting to kind of compensate for that. And so we'll end up, say if the trim strings were swinging this way, we would end up pushing in the opposite. We want to put a bit of right pedal in, and that will bring it round to the correct way, so we're flying in trim again. This grip on the end of the collective, this is the throttle control, and so we can roll it outboard like that or away from us, that's to increase the throttle, and we can roll it in or close to ourselves, that is to close the throttle. So outboard for more, and close to ourselves to close or reduce the throttle. As we already talked about, there is the correlator, which is connected to the movement of the collective. That's already increasing and decreasing the throttle. This control here is more for fine control, but we have something else called the governor, which is an electronic device. It senses the RPMs in the engine, and it makes fine adjustments of the throttle for you to make sure that the RPMs stay at the correct level. And we have a little switch on the end here. You just see this little tiny switch here. This is to turn the governor on and off. And in normal flight, you always want that governor on. You want the governor to do its job, to make those fine adjustments for you. And if we look down on the instrument panel here, we have a little warning light to tell us when the governor's off. We should never be flying with that coming on. So what would normally happen is, as we've started the engine, we'd be at an idle speed, and when the engine's warm enough, we will roll the throttle on, making sure the governor's on, and at about 80% engine RPM, the governor takes over, and then you'll feel it roll this throttle up to the correct level, and it will move underneath your hand, because you should be able to just let this throttle move under your hand. You can override it if you need to, if there's a malfunction in the governor, but a death grip on this thing will cause over or under speeds. You've got to let this governor move the throttle for itself. So we talked about how the correlator kind of asks for more power, and this governor or throttle makes the fine RPM adjustment. If we look over on the instrument panel, I'll show you what these instruments would show. So as we increase if we pull the collective up, we're asking for the engine to produce more power, and that's shown on the manifold pressure. So as we pull more power, the throttle opens and the power level goes up here. And we'll talk more about this in later videos. And then these RPMs should always stay in the green up here, and that's what the governor's doing. So the governor is adjusting this little throttle control on the end to keep those RPMs where they should be. And then in the future we'll talk about auto rotations and things like that, where we manually mess around with the throttle. Okay, so I'm going to show you how this collective collectively changes all the blades at the same time to increase the pitch. So I'm going to be moving this up and down, and then I'll show you on the blade what's happening there. We've pushed this blade down close to the ground so you can see it. So I'm pulling the collective all the way up there, and then I'm lowering the collective all the way down. And you can see on the blade closest to you that that's increasing the pitch and decreasing the pitch. And if you can see the blade on the other side, it will be doing the same. You can see it from there. So increasing the pitch, decreasing the pitch. So that's the collective collectively moving all of the blades at the same time. Okay, so I'm going to demonstrate the movement of the cyclic and how that moves what's called the swash plate, and then how it moves the blades individually. So if you go up and look up at the swash plate, and what I'll be showing you is I'm now going to be moving the cyclic forward and backwards. You can see the swash plate is moving the way that I'm moving the controls, and also the way that the disc is going to move. And now if I do left and right, now if I do a complete circle, you'll see the entire swash plate move around in a complete circle. And you can see those linkages moving the pitch of the blades. And what we're going to do is we're going to hold a forward control position, and then we're going to move the blade round so you can see how it changes the pitch individually at different amounts as it moves the blade around the circle.
What we're attempting to show here is how the blades individually change pitch position along the path of the rotor disc plane, and each blade is going to be in a different position. This one, as we follow it around, hopefully we can see this. You can see that right now the leading edge is pointed down, and as we go, it's going to change all along the way. It's at a different angle. By the time we get around the other side, it's actually going to be pointed up rather than down, and the other blade is doing just the opposite. So see how it's moving up.
Right, so we're talking about the anti-torque pedals and how they yaw the helicopter by changing thrust produced by this tail rotor, and they do it by changing the pitch. As you can see the pitch change here of this tail rotor blade, so it increases its thrust one way or even thrust the other way. Right, so right pedal right, left pedal left, all done by changes in the pitch of this main rotor system, the tail rotor system.
Alright, so if you want more information, you can check out the Robinson R22 Pilot Operating Handbook, which is now available from Robinson to download. You also got the Rotorcraft and the new Helicopter Flying Handbook from the FAA. That has a flight control section. Again, those are available to download. You also got the ASA Helicopter Oral Exam Guide and the ASA Private Test Prep to check out. There's also a Robinson R22 Maintenance Manual you can download from Robinson if you check out Chapter 8. And then finally we had those couple of videos that I was talking about, the first one being the Fokker-Wulf FW61 video, which is being flown inside a stadium, and the other one is the Sikorsky S52 loop video, both worth checking out. Just click on those links below. Thanks very much for listening. Any comments, any ideas, suggestions, please send them on, and we'll see you next time.